Okay, now I'm unmuted. Hello, everyone. Great to be here. And as Ariana said, I'll talk a bit about connecting quantum computers to HPC systems and why we would want to do that and what we can gain from this. And I'll use this LUMI-Q as an example, and LUMI-Q is one of these 6 consortia that Ariana mentioned there that will soon start setting up throughout Europe these HPC plus QC systems to the benefit of everyone in Europe. So it's under this EuroHPC project. So even if one is not part of this consortium, one will anyway get access to the quantum computers, which is I think a real advantage for Europe. Okay. And we'll be giving this from the perspective of an HPC center, a bit like Ariana, of course. Well, I'm representing CSC up in Finland, and well, suffices to say at this stage that well, we've been providing supercomputing services for over 50 years. We started with the UNIVAC 1108, and now the latest and greatest addition to the panelists that we are hosting, the 10-country LUMI supercomputer, and we are almost 600 employees and do plenty of other stuff than supercomputing as well, but supercomputing is and quantum accelerated supercomputing is the topic of today. But I'll start with a few definitions first. So what is a quantum computer? Well, as we already heard, a quantum computer is a device that directly exploits quantum mechanical phenomena to perform some calculation. And these quantum mechanical phenomena are superposition, entanglement, wave function phase, and those are the 3 main ones as we heard. So this is a very simple definition of a quantum computer, just thinking of at a very high level of what it is. But immediately it's also very useful to be clear about what a quantum computer is not. And a quantum computer is not some super fast version of a classical computer. It's completely different. It's not doing at all the same thing. So in practice, it means that it speeds up some types of calculations, but other types of calculations it will not speed up at all. This means that quantum computers really can potentially excel at certain computational tasks, but not for all tasks. So they will always need cooperation with a classical computer. This is the central message here of the beginning of this talk. So quantum computers are not going to replace supercomputers. They will work side by side. But already now, quantum computers are more powerful than supercomputers for some tasks. The slight caveat is that none of these tasks are useful. So well, it's more of proof of concept demonstrations that in principle quantum computers actually can do things that supercomputers cannot emulate or simulate. To get to so-called quantum advantage, we'll talk more about that in a moment. We will need many more and also better qubits than what are available now. But quantum computing is big, and all major players in the world, nations and large IT companies, are involved in quantum computing. If not all, then almost everyone. We heard already about IBM, Google, Intel, Alibaba, Amazon, Microsoft are all developing some sort of quantum computing products, quantum computers or software. In Europe, the situation is a bit different. Here, all of this quantum computing activity is almost purely startup driven. So we don't really have many of the large companies involved in, for example, building quantum computers or building quantum software. This of course gives Europe an advantage in being very flexible and agile in operations, but it also places some constraints and challenges for scaling up the operations, and of course there's always a risk of being just bought out when you're a small startup. But I think in general we are doing quite well in the scene here in Europe. And just to put things in a bit of perspective where we are now, so the largest quantum computer, general purpose quantum computer, as defined by qubit count, is now in the hands of IBM, where the Osprey QPU now has over 400 qubits. And foreseeing a bit of the timeline, so both IBM and Google estimate that quantum computing will be industrially relevant by the end of this decade. So not yet, but soon. So what will happen next is that quantum computers will merge with supercomputers, and actually the more powerful the quantum computer is, the more powerful also the classical counterpart needs to be. Classical HPC is needed for many portions of an entire computational workflow when you involve quantum computers. So first of all, well, as mentioned, so quantum computers are good at a few things, and they are really good at those, but then other things they are not good at all. And in practice, it means that for any sort of a real world modeling workflow, there's always parts that just are much better computed with the classical computers, even if you would have a very powerful quantum computer. So those parts of the workflows that cannot run efficiently on quantum computers will always need some supercomputing capacity. Supercomputers will soon also be needed for controlling and orchestrating parallel quantum computing. Already now, one needs a classical computer, of course, to control the operations of a quantum computer, but the more complex this becomes, the more complex also, or more powerful classical computing capacity will be needed to do this efficiently. But another thing that doesn't really come up in classical computations at all is error mitigation. So quantum computers are actually of rather low quality, to say it like this. So they compute wrong very much, and the outputs from them are very noisy and of low quality. But one can remedy this by classical means with so-called error mitigation and other techniques. A bit like if you have taken a picture with your camera in a very dimly lit room or something, and then well, you get a blurry bad quality picture, but already now with some image processing software you can really touch up that picture very nicely with post processing. And what it in practice does is that it removes the errors from your signaling of your device, and well, a bit of an analogous way you can also do that then for the results that you get from quantum computers. And another thing is also programming for quantum computers, and especially compiling programs for quantum computers. So to be able to do this efficiently will actually require lots of processing power. We'll probably hear a bit more about this in the next talk, but just quickly here listed some of the major application fields where this HPC plus QC combination is expected to be efficient. Well, one is this machine learning artificial intelligence, where both actually can help each other. One can, for example, use these classical machine learning methods to decrease the noise, and then there are quantum algorithms for machine learning that can really enhance the machine learning efficiency as well. Financial applications, optimization and logistics and so forth are often brought up as example where quantum computing will be useful for good reason. And then we have, Ariana already mentioned, material science and chemistry, including the pharmaceutical industry. So they're studying the electronic structure of molecules and materials is really a hard problem for classical computers, but in principle simple for quantum computers. Another thing that will happen next is that this quantum software part will become the dominant way that we look at things. So So just as in classical IT, so the biggest money lies in actually use cases and software, nothing built in the actual system. So Intel and AMD are big, but Amazon and Google are 10 times bigger. So we are already seeing this upcoming shift from the hardware market to software. So why are we interested in quantum computing? Well, as an HPC center, the main reason is that we need to start working on this integration of HPCs and quantum computers as soon as possible. Our end users needs early access so that they can make their existing workflows quantum ready, so to say. Here, this transition to also include QPUs, quantum processing units, will be, well, arduous. The transition from just classical CPUs to GPUs has been going on for over a decade, and there's still plenty of program packages and software that hasn't been ported to GPUs, even if one would get an immediate speed up there. So we expect that there will be plenty of work ahead of us before we have any sort of useful software running on the QPUs. And the main reason is that if we want to do something on quantum computer, we really need to rethink our problem from scratch and figure out how to use these new capabilities that quantum computers provide. And here HPC centers serve as a natural starting point for this work, because usually HPC centers already have the basic services of performing some sort of advanced calculation in place. So user authentication, administration, and resource allocation, and of course storage systems, high-speed networks, and the classical resources. And another resource that HPC centers has is the end users, those that really are doing high-end modeling that require plenty of computing power. So we need the end users to prepare for this upcoming shift to quantum computing, but we cannot do this work alone. So there's plenty of development that is required for this, and it's not the job only of HPC centers to do this. It also requires plenty of basic research still to get quantum computing going, and that's also not really the domain of HPC centers in general. So we need to somehow get the end users, both from academia and industry, to jump on the quantum train, so that we can get this going. And for this, we need some carrots, some reason for the new user groups to start looking into this. But first, we really need to set up this computational infrastructure so that there is some tools for the new users to actually use and try out and develop a platform to develop on. And here's just quickly a few slides of how one could connect HPC systems and quantum computers, divided into 3 different categories, depending on or with increasing complexity of the software stack that needs to be developed. And the easiest one is this standalone, where one just has cloud access to a quantum computer. And then the next one is to have a co-located on-premise approach, where we have the quantum computer sitting next to the HPC system. And then the third category, which LUMI-Q also is targeting, is this distributed approach, where the QPUs and the HPC resources are physically distant, but these orange servers here, as you can see, so they anyway represent classical resources of sufficient capacity that are placed next to the quantum computer. So they are powerful servers, but they are not true HPC systems. And the software stack for building up this sort of distributed approach requires a bit more work than the maybe more straightforward co-located approach. And that's just because we need to take care of one additional communication step between the classical box here, the orange one. I don't know if you see the cursor here, but I hope you do. But anyway, between the classical orange box and the HPC system to one side, and then the quantum computer to the other side. So while if you have the co-located, we can jump over this extra communication step. And that's not completely trivial to set up this communication. User authentication also needs to be done twice if we have the quantum computer in another site than the HPC center, but that's rather trivial to take care of. And then, well, of course, you also need personnel at more than one physical location, because neither quantum computers or HPC systems still run as robots without any human intervention. So why would one make then this distributed system if it's a bit more complicated? Well, the reason is that when you have this software stack in place, it's easy to add additional quantum computing resources into your infrastructure and into your platform, because the only thing you need is location of a classical server next to the QPU that you want to integrate. And this really increases diversity and inclusiveness of the entire system, because users can then access several QPUs from the same computing environment. It also facilitates this time sharing of QPU resources. So few HPC centers can buy, for example, 5 different quantum computers. Ariana showed there nicely towards the end that quantum computers can be implemented in many different ways, and they all behave slightly differently, but they are also very expensive creatures. So it's usually much more efficient to have part-time access to many quantum computers than full access to just one type of quantum computer. So you can share your QPU resources much more simply, but still in an efficient manner within this distributed approach. And then the last point here that I want to bring up is that quantum computers and HPC systems require or have very different requirements for the data center environment. So HPC really needs large data centers that have sufficient and affordable electric power, otherwise they are quite robust. But quantum computers, again, really need very shielded environments, so they are very sensitive to temperature changes, vibrations, electromagnetic fields, other sources of noise, and so forth. And then actually, recently, there was also published this article that got some people a bit worried that already now apparently cosmic radiation is starting to affect the qubits unless one have them in really shielded places. And then, well, if one needs to start digging down the quantum computers underground or put them behind heavy metal shieldings, then one might not want to do that for the entire HPC system. So there are reasons why a distributed network of this HPC and QC is worth the trouble of setting up the software stack. And here we come a bit to the quantum computing with the LUMI infrastructure. So where also users from Belgium, of course, already are running on the LUMI supercomputer itself. But here, more perspective on what we are doing on the quantum computing side in a prototype manner. So it's now a year since we ran the first quantum job through the LUMI queuing system, and there we actually connected the LUMI that is now up in the northern Finland in Kajaani to the Cal 9000 quantum computer in the Chalmers University in Sweden. A bit later, we also connected LUMI to the Finnish quantum computer developed by VTT and IQM, and have now integrated it fully with the HPC environment, so identity management and resource allocation and other HPC resources and so forth. And next, what we want to do is to implement the LUMI-Q concept of this pan-European distributed HPC plus NQC environment, where we have several N number of quantum computers. So we really want to combine several HPC resources and several quantum resources in a unified manner. And here's a map of the LUMI-Q consortium and then what we have available here. And so I can see here first that, okay, it's a large consortium. There's 14 partners in it from 9 countries in total, plus collaborators. But the idea anyway is to really connect all of these resources together in a unified manner and make them available to the users throughout Europe. And here's a bit of a technical view of how this looks like. So the idea is that, well, the quantum computer procured within this project will go to the Czech Republic and be placed in the IT4I data center with Carolina. But then we build up the software stack in this manner, and then we build one software stack which connects, well, the Carolina supercomputer to the LUMI-Q quantum computer. That's the idea of the project, but we do it in a manner that all of these other resources can then be plugged in a more or less plug and play manner after we have built up the software stack in a suitable manner. So, okay, and then, well, a bit about the user experience. There's a bit of time left. So, as a precursor to this, so as mentioned, so we connected the LUMI and the Helmi quantum computer, and it has actually been open now since November last year for academic users, non-commercial use, and there's already been running and is running several different projects here and related to quantum machine learning, error correction, and education also, and so forth. And the main take back from our initial survey of how the users have seen this is that, well, it really is a big difference between using a real quantum computer and using a simulator. So the question is, what can you do with 5 real qubits? And well, the answer is that we can really learn how to use real quantum computers. And the idea is that quantum computers are very different from traditional quantum computers. Okay, traditional classical computers, we should say. And we have a completely different programming paradigm, as we heard already. And quantum computers are different from each other. They are, well, they are different from themselves in the way that running the same program twice will in general give you different answers on a quantum computer. And also quantum computers compute wrong most of the time. So experienced HPC users will really see a large change necessary to actually learn how to use quantum computers. So one is used to this classical computers and supercomputers to being highly reliable and computing right all the time, and even small problems really cause lots of concerns. But a quantum computer, on the other hand, is really a device for experiments. So this means that one needs to be critical towards the results one gets in a completely new way, and one needs to get this feel for how to actually perform successful calculations, because they are, in practice, they are more like experiments than computer calculations when you do something on a quantum computer. And this is a rather big shift in thinking that is needed in the user base. So how should we get users to jump on this wagon of trying to start using quantum computers? Well, I think that we really have to provide the end users with some prospect of quantum advantage. And now the question is that, can we do this at this stage? If you think of end users who mainly are interested in using quantum computing as a tool for science or development, research and development, quantum advantage is maybe at this stage not obvious. And they might ask the question of why should one invest resources on quantum computing when it might not give immediate returns? But again, then it means that we first need to define what quantum advantage actually is. And one definition, and the one that you usually encounter first, is that this wall time quantum advantage that I marked this here. So which means that quantum computers help solve problems faster than if you would have just a classical HPC system alone. So, and we are actually still some time away from this. We need, in addition to hardware developments, there's also a massive need for quantum algorithm and software development before we get here. But the second one is the green quantum advantage, where the definition here is that when we use a quantum computer, we get a higher solved problem per watt ratio. So what this means is that the QPUs don't need to compute things faster than HPC, they can do it slower, but using less energy. And this is already an advantage. So if you could solve the same problem, even if it takes 10 times longer, but uses just 1% of the total energy, then that's an advantage in most cases. But okay, here one needs to also look out that one needs to really think of all the energy that is used in the problem. But that's more or less evident when one starts doing this. Then there can be this quantum quality advantage, and this would mean that the quantum computer somehow provides more accurate, or by some other measure better quality predictions. And this would come from the fact that quantum computers really solve problems in a completely different manner. And this is also possible already at moderate qubit counts, before QPUs perhaps do things faster than classical systems, but just because they do things differently, they might come up with different solutions to the same problem, and hopefully that is then also a better solution. Maybe not always, at least. And then we have this quantum control advantage, and if you think of this, then quantum computers actually provide really high-level control of quantum systems. So it's a highly controllable environment for manipulating quantum objects. And this means that we actually can study fundamental physics, for example, at a completely new level of accuracy. So this would fall into the category that one is actually not performing computation at all on a quantum computer, but rather uses quantum computers really as a physics lab. And then there's category other quantum advantage, which could then be everything else. And for academia, the carrot could be, for example, scientific publications and project funding, and for industrial users, then competence development and early creation of intellectual property. And of course, one should not underestimate the value also of PR. Being involved in quantum computing, of course, shows that the company is at the edge of high technology. I'm running out of time, so I just want to quickly mention these non-computing applications. So this is where you use the quantum computer for other things than producing results of a modeling workflow. And one can, for example, create time crystals or wormholes on QPUs already now. And here's just to show that, yes, the amount of articles related to this field is growing exponentially. And just to finish here with a small timeline of quantum advantage. And if you think of this other quantum advantage, this was the last one with project funding, scientific articles, early IP creation. So that's happening already now. So we have that quantum advantage here already. We also have the quantum control advantage already. So we can now, with the QPUs that are available, do these types of physics experiments that were impossible to do before. So it is actually a rather important group of users that can see advantage from quantum computers and using them right now. And then the others, quantum quality advantage. You can choose the unit of time yourself here, but I've just ordered them here in some sort of a increasing order of how long we have to wait for these things. But here the main point maybe is that all of these are coming, but some of them we already have now, and that's I think an important point. I'll just leave this up here for browsing and stop here as I'm over time. Thank you.